Where does the cross product come from? If I have two vectors A and B and I cross them, it gives us a vector. So the result of the cross product is a vector, and by definition, it is a vector that is orthogonal to the two vectors that we were crossing. And we want to look at where that formula comes from. And I'm going to use the dot product to derive it. I'm not going to go into the dot product. If you're not familiar with it, you might want to stop and research that and come back. But one thing that's well known about the dot product, and these are the two kind of so-called multiplications we can do with vectors, the dot product and the cross product. But the characteristic of the dot product we want to use is that when you dot two vectors that are orthogonal, right angles to each other, you're going to get zero. You're always going to get zero. And so our strategy is to force A and U to be orthogonal by dotting them and making it zero. And this is the dot product operation. And same thing with B and U, we make those orthogonal. And so I have a system here that I need to solve for X, Y, and Z. So here's the system, and now it's just algebra. We have a three variable system. Well, how should I say this? It's three variables, only two equations. So there's going to be infinite answers. You may remember that from algebra. And the way that plays out with the cross product vector is just that its length can be an infinite number of different lengths. So that's how that plays out. But basically, what my strategy is going to be is to solve for X and solve for Y in terms of Z. So I have a coefficient times Z, coefficient times Z. And so to solve for X, I need to get rid of the Y's. And so that's why I have this A2 and B2 I'm multiplying through so that when I subtract these two equations, the Y's go away. They have the same coefficient here. And I only have X stuff and Z stuff. And then I go ahead and solve for X, and I get what I wanted. I have X in terms of Z. Then I do the whole thing over again and solve for Y in terms of Z by simply taking the X coefficients, doing multiplication, subtracting the equations, do everything I did here, and I get this. Well, now this is basically the cross product, the vector that is the cross product, but it's ugly looking. So I have the X part, the Y part, and then Z is just Z. You may remember doing this in algebra as well when you have infinite solutions. So you make X and Y in terms of Z. And so that's all I've done here. So now this is a vector that I don't like the way it looks. I'm going to clean it up. So I'm going to take this denominator and multiply through the vector by this. So it will cancel with this and I just get this. And then this will cancel with this and I'll get this. But notice for this middle one, this is backwards to this. And so all I need to do to overcome that is just negatize it. I don't know if that's a word, but I like saying it. And that way I could flip this. So, but basically what I'm going to do is put it up here. And now this here will be flipped and those will cancel. And I'll just get this, but then of course I distribute the negative in to get this. And then this times Z and I get this. So we have a better looking vector now. I'm going to pull the Z out front. Now this is just nothing but a scalar. It's typical to just make Z1. This is where we could make an infinite number of vectors that they're going to point the same way. They're just going to be different lengths. Well, when you hear the cross product mentioned with no qualifiers, it means this part in red. It's customary to just choose to make this a 1 and then we ignore it. and this is the cross product. Now this is hard to remember. So when you look at videos on how to take a cross product, typically what they recommend is think of this as a determinant, because it just so happens a determinant does the same exact thing. And so you make a dummy vector ijk, and then you put your a and b vectors here. And then the determinant process says take this times this submatrix, well, times the determinant of this submatrix, and that would be this. And then take the opposite sign of this times this submatrix, times the determinant of this submatrix, and that gives you this. That negative happens for the reason that I mentioned above. And then this times the determinant of this submatrix, and that gives you this. And there we go. That's it. The only thing I did here is I just don't really like that negative being there, so I flipped these and made this a plus, so I can have all pluses here. So this is just another way of writing a vector if you're familiar with vectors, which if you're looking here to find out about the cross product, you probably are. And that is where the cross product comes from.